Hello, here is the question number 17 that reads a conducting rod of mass m and length L is suspended horizontally with the help of two identical non-conducting springs, each of a stiffness K, in the uniform horizontal magnetic field B. The rod can slide between two fixed frictionless vertical conducting guides, and an uncharged capacitor of capacitance C is connected between the guides as shown in the figure. Find the time period of oscillation of the rod, neglect resistance and inductance in the circuit, and assume acceleration of free fall to be g. So this is the picture. This horizontal is the rod of which is conducting mass m length L. This is conducting guides so that it keeps this rod horizontal, and these are non-conducting springs and the magnetic field existing outwards, and this is connecting a circuit, and with the circuit C capacitor is connected, which is uncharged. Now initially you'll find this spring and this entire system, this conducting rod will be in equilibrium. So when they are in equilibrium, then you'll find, let's say, elongation in the spring is x naught. So you'll find kx naught must be equal to mg. Kx naught from here, kx naught from here. That means 2kx naught must be equal to mg. So 2kx naught equal to mg. This is the equilibrium condition that we already know. Now let's consider that this rod has come down by a distance x from this equilibrium position, and it's moving downwards with velocity v. So this picture I have drawn, let's say this black color line was the equilibrium position, and then this conducting rod has come downward and it's further moving down with velocity v. This is the magnetic field. Now when it is moving downward, so then you find this the area inside is going to change. That means the flux through this circuit is going to change. Now due to change in this flux, you will find there's going to be induced EMF coming in, or you can say this conducting wire is moving in a magnetic field, so that this will have induced electric EMF. This induced EMF is going to be BL into V. So this because of that, you'll find there's going to current in the circuit. Moreover, we can decide the direction of current because this flux is going to increase, so this the current will be in such that so it will oppose this cause. That means the current will be in this sense. That means it is going to be in anti-clockwise sense. That means the conducting wire, you'll find current running like this, as I've shown over here. I've written there, due to decreasing flux in the circuit, induced current will be in anti-clockwise sense. Yes. Now because of this current, now you will find this conducting wire of length L is moving with velocity v and has a current, and it has present in a magnetic field. So there is going to be a force acting like IL cross B, ILB force, and that ILB force will be acting as per the right hand rule, upward direction. So you'll find the restoring force will be given by two forces will be this due to the spring, so will be identical. It will be like k x naught plus x, that's total elongation, into 2, that means due to both the springs, plus ILB is going to because of the current through this conductor, minus mg, gravity will be acting downwards, so this will be the net force. But we know at equilibrium 2kx naught was equal to mg, so 2kx naught mg will get cancelled out. Effectively, restoring force is going to be 2kx plus ILB. Now we need to find this current at any instant of time or at the location x. So for that, use this electrical circuit. This is going to behave like electrical circuit, like EMF, that's battery, and then this capacitor, this current I is running and Q charge is there. So Kirchhoff equation will say Q by C must be equal to E, which is BL into V. Now Q could be written as BLC into V. C comes here, right? Now differentiate it, so it's become dq by dt, which will be like BLC into dv by dt. Now we know dv by dt is downside and force is acting upwards, so you will find this will be like retarded